On this question, we want to determine the real solutions to the system of nonlinear equations. We have the system x squared minus 4y squared plus 60 equals 0, and 4x squared plus y squared equals 32. When I start systems of nonlinear equations, I like to get a visual representation so I can get an idea of how many solutions I might be looking for. So looking at these two equations, these are equations that we really haven't studied the graphs of in this class. You would study these graphs in a pre-calculus class. So these two are going to be a hyperbola and an ellipse. And a hyperbola has a picture, kind of looks like two parabolas that are facing away from each other. And ellipse would be like an oval. So if we were to think of these in the same coordinate plane, we could get 4 solutions to this system. We could get 3 solutions if our hyperbola and ellipse are just touching each other in that way. So we could have 4, we could have 3. We could make it so that we have just 2 solutions, if it's something like this. 2 intersection points. We could draw it so that we just have 1 solution just touching. And we could make it so that there is no intersection point. So as we solve this system, we might have 4 solutions all the way down to no solution. So then I'm thinking of the methods that I typically use to solve systems. We have the substitution and the elimination method. We could use either one of those. Let's try this with the elimination method. With the elimination method, we need all the like terms to be lined up, and especially we want the equal sign to be lined up. So the only thing that's not lined up right now with like terms is our constants. So I'll move that 60 to the other side, and that would give x squared minus 4y squared equals negative 60. Then I have 4x squared plus y squared equals 32. And now my like terms are lined up and my equal sign is lined up. And if I want to use the elimination method, I can eliminate x or y. I'm going to choose to eliminate y because I already have the opposite signs in front of y, and I only need to focus on the coefficient. So I want that coefficient on the y squared to be a 4. So I'll multiply the second equation by 4 to make that happen. So our first equation is remaining the same, and our second equation becomes 16x squared plus 4y squared equals, and let's see, 32 times 4 would be 128. So now I'm able to add those equations together, and that would give me 17x squared. The y's eliminate, and I need to do 128. Whoops. 128 minus 60, that would be a 68. So I'll continue solving this by dividing both sides by 17. And does 68 divide into 17 evenly? let's see, 68 divided by 17 is 4. And I have x squared equals 4. We're going to square root both sides. That gives x equals plus or minus 2. So we found the x coordinate of our ordered pairs. And we'll substitute this in to get the y coordinate. And you can substitute it into any equation that has two variables. So I can use the two original. I can use these ones that I've modified here. Any equation with two variables. So I'll use that first equation, x squared minus 4y squared plus 60 equals 0. So if x is a 2 or a negative 2, this is going to come out the same. So I can actually do this at the same time. Plus and minus 2 squared minus 4y squared plus 60 equals 0. So a positive 2 squared is 4, a negative 2 squared is 4, and that's why I was able to do those both at the same time, because it's coming out the same. So that's 4 minus 4y squared plus 60 equals 0. That's negative 4y squared plus 64 equals 0. Solve for y by subtracting 64 on both sides. The negative y squared equals negative 64. I'll divide by negative 4. That's y squared equals positive 16. Square root both sides. And that'll give y equals plus and minus 4. Let me zoom out a little bit just to give us a little bit more space. So remember, we started with our x coordinates of plus and minus 2, and we got y coordinates of plus and minus 4. So this is going to give us our 4 solutions: a positive 2 with a positive 4, a positive 2 with a negative 4, a negative 2 with a positive 4, and a negative 2 with a negative 4. So these are the solutions to our system of nonlinear equations. For this one, we want to determine the real solutions to the system of the nonlinear equations. We have 2x squared plus y squared equals 6, and x squared minus 2y squared equals negative 15. So on this example, I can use either the substitution method or the elimination method. This is really similar to the example that we just did. Since we used the elimination method in the previous example, let's try the substitution method on this one. So for the substitution method, we need to have some like terms that match in either equation. So I notice that I have a matching x squared in both equations. So I know I'm going to be able to solve for one and substitute into the other. And I also have a matching y squared in both equations. So I could also solve for y squared and substitute into y squared. To me, it looks like the easiest way to do this would be to solve for this x squared in the second equation. So let's start with that. We have x squared minus 2y squared equals negative 15. I'm going to solve for x squared by adding 2y squared to both sides. We have x squared equals 2y squared minus 15. So I've solved for x squared, and I'm going to substitute that into the other equation. I'm going to substitute this into the x squared. And that would give 2 times 2y squared minus 15 plus y squared equals 6. I'll get rid of the parentheses using the distributive property. We'll distribute that 2 to both terms. That gives 4y squared minus 30 plus y squared equals 6. I can combine like terms, giving me 5y squared minus 30 equals 6. I'm going to add 30 to both sides, and that gives 5y squared equals 36. I'm just going to pause here for a second, just double checking my work. Okay, so we'll divide both sides by 5. That gives y squared equals 36 over 5. And I can take the square root of both sides to get y equals plus and minus 6 over the square root of 5. Square root of 36 is 6. And we have the y coordinate of our ordered pairs, and I can substitute this in to get the x coordinate. So I'm going to substitute into this equation here because it's partially solved for x. We have x squared equals 2y squared minus 15. And x squared equals 2 times, and I can do plus and minus at the same time, 6 over square root of 5 squared minus 15. I can do that plus and minus at the same time because I'm squaring it, so both the positive and the negative answer will come out the same. So that's going to give 36 over 5, 6 over square root of 5 squared. I square the 6. 6 squared is 36, and square the square root. They cancel, giving me the 5. So then 36 times 3 is 108. So I have 108 over 5 minus 15 equals x squared. And in order to add these together, I need to get a common denominator. So for the 15, I'll multiply by 5 over 5 to get that common denominator. So 15 times 5 is 75. And 108 minus 75 is 33. We have 33 over 5. So finally, I'll get x by itself by square rooting both sides. And we get x equals plus and minus square root of 33 over 5. So remember, we started with a y coordinate of plus and minus 6 over square root of 5. We ended up with x coordinates of plus and minus square root of 33 over 5. So let's write those ordered pairs. We have a positive square root of 33 over 5. And we'll do a positive 6 over square root of 5. This square root symbol, I drew it incorrectly. The square root should be over the whole fraction. So let me fix that. And then we have positive square root of 33 over 5 and negative square root of 6 over square root of 5. Square root of 33 over 5, this one should be negative. We'll have a positive 6 over square root of 5, and a negative square root of 33 over 5, and a negative 6 over square root of 5. So that would be our 4 solutions. Okay, so I'm going to come back here, and I do have a mistake in my work. And right here, I changed this 2 to a 3 for who knows what reason. And this would be a 2, and 2 times 36 would be 72. And then when I get a common denominator, 72 minus 75 gives me a negative right here. And that would be a negative 3 over 5. And negative 3 over 5 underneath the square root gives imaginary solutions. So that would be plus and minus I square root of 3 over 5. So with imaginary solutions, we have no real solutions, and there would be no real solutions to the system. So in the imaginary world or complex world, we do have solutions, and those would be plus I square root of 3 over 5, comma 6 over square root of 5. And then here we would have an I square root of 3 over 5, a negative I square root of 3 over 5, and a negative I square root of 3 over 5. So, but looking for only real solutions, we have no solution. On this question, we want to solve the exponential equation 9 times 11 minus 3 to the 3x minus 5 equals 10. Now, to solve the exponential equation, we first need to isolate this exponential part. We've got all of these other operations on the left-hand side, so before we can use any of those techniques that we have for solving exponential equations, we have to isolate that exponential portion. So I'm going to start by dividing both sides by 9. And that will give 11 minus 3 to the 3x minus 5 equals 10 over 9. And then I'll subtract 11 on both sides. And I've got negative 3 to the 3x minus 5 equals 10 over 9 minus 11. I want to combine these together and get a common denominator. So I've got 11 over 1, and I'll multiply by 9 over 9. So that will give negative 3 to the 3x minus 5 equals 10 over 9 minus 99 over 9. And that's negative 3 to the 3x minus 5 equals negative 89 over 9. I'll get rid of that negative by dividing by negative 1 on both sides, and that finally has my exponential expression isolated. 3 to the 3x minus 5 equals 89 over 9. So now we can use one of our techniques for solving exponential equations. There's 3 that I keep in mind all the time. Making the bases the same, which we're not going to use on this example. Converting to a logarithm, or taking the log of both sides are both options in this example. I prefer to take the log of both sides because it's easier to type in the calculator if you have natural log, which usually is on the home screen of your calculator. So I'm going to do the natural log on the left. Natural log 3 to the 3x minus 5 equals natural log of 89 over 9. This allows me to use the power rule for logarithms. And I would have 3x minus 5 times natural log of 3 equals natural log of 89 over 9. Then I need to get rid of these parentheses using the distributive property. of 3x natural log of 3 minus 5 natural log of 3 equals natural log of 89 over 9. And now I can work on isolating x. I'll add 5 natural log of 3 to both sides. And that gives 3x natural log of 3 equals natural log of 89 over 9 plus 5 natural log of 3. And to isolate x, I'll divide by 3 natural log of 3 on both sides. I have x equals natural log of 89 over 9 plus 5 natural log of 3 divided by 3 natural log of 3. And this is the exact solution to our exponential equation. Let's zoom out so we can see the whole thing at once. So I brought my calculator up here to type this in the calculator. And as I said, I chose this method of taking the log of both sides because I've got natural log on my home screen. So to type this in the calculator, we need to make sure that we put parentheses around the whole numerator so that your calculator knows which expression goes in the numerator and which goes in the denominator. So we're going to do parentheses, natural log of 89. That should be 89 over 9 plus 5 natural log of 3. We're going to close parenthesis for that log, close parenthesis for the whole numerator. Then we're going to divide. And in the denominator, I also need parentheses to make sure the calculator knows that all of that 3 natural log of 3 is in the denominator. And I close parenthesis for the log and close parenthesis for the denominator. So we get an approximate value of, let's round to, say, 3 decimal places. That would be 2.362. So that's our approximate value of the solution. On this question, we want to sketch the logarithmic function, label 3 points that lie on the graph, and determine the domain and the equation of any vertical asymptotes. We'd like to do this for h of x equals log base 8 of x. So we want to start by finding 3 ordered pairs that are on this graph. And typically, I have a standard set of x's that I choose to substitute in. But if I choose just any random x coordinates, I'm going to get y values that have decimal values, and I would really prefer to have nice ordered pairs that I can plot on this picture. So I'm going to try to be very strategic about what x's I choose, and the way I can be strategic with logs is to pay attention to that base. So if you want to be strategic about this, you're going to pick the base of 8 to the powers that you would normally choose as x's. So I would normally choose like -1, 0, and 1 as my x's, but because of that base of 8, I'm going to choose as my x's 8 to the -1, which is 1/8, 8 to the 0, which is 1, and 8 to the first, which is 8. So if I choose these values, then my y values will come out to be nice numbers. So then I want to find the y, which is going to be log base 8 of 1/8. And that's going to give me a y value of -1. This is the y value here. Log base 8 of 1 will give me a y value of 0, and log base 8 of 8 gives me a y value of 1. So notice these end up being the y values. So then I have this list of ordered pairs, 1/8 and -1, 1 and 0, 8 and 1. So this is going to allow me to get a sketch of the graph. So 1/8 and -1 would be about here, 1, 0 here, and 8, 1. Would be about right here. So our logarithm takes the shape, almost looks like a square root, but the square root stops at 0. This one has a vertical asymptote, which gets closer to 0, but it doesn't stop at 0. So we're going to have a vertical asymptote that happens at the vertical line x equals 0, which is one of the things that they asked us about here. And the other thing they asked us about is to find the domain. For a logarithmic function, you can only substitute positive values into the logarithm, and that's reflected in our picture here. If we look to the right of 0, which is where the positive values are, we can see our graph. But when we look to the left, there's no portion of the graph. So our domain is going to be 0 to infinity. That's written in interval notation for the domain. So we've got 3 points on the graph, the domain, and also the vertical asymptote. On this example, we want to sketch the logarithmic function, label 3 points that lie on the graph, determine the domain, and the equation of the vertical asymptote. And this time we have another log equation, a log function, but with a fractional base. So that's g of x equals log base 1/14 of x. So I want to start by getting those points. And as we said before, usually I have a standard set of x's that I choose, but I want my ordered pairs to be nice numbers. So I'm going to use that base of 1/14 to the -1 power, and that would give me 14. The negative in the exponent does the reciprocal of the base. And we have 1/14 to the 0 power would be 1, and 1/14 to the first power would be 1/14. So then I'll find my y values. Log base 1/14 of 14 is going to give me this -1. Log base 1/14 of 1 will give me 0, and log base 1/14 of 1/14 will give me 1. So this gives me ordered pairs of 14, -1, 1, 0, and 1/14, 1. So sketching the graph of that, I'm going to have to go 14, 14 and 1, sorry, 14 and -1, 1, 0, 1/14 and 1, gives me a graph that looks like this. We still have a vertical asymptote that is right on top of that y-axis, that's the line x equals 0. And the domain, once again on this one, is going to be positive values, 0 to infinity. We can only take the log of positive values. Alright, so this question, we are going to find the real solutions to the system of nonlinear equations. We have x squared plus y squared equals 36, y squared minus 2x equals 36. And I do like to draw a picture just to get an idea of how many solutions I might have. The first equation is a circle, and the second equation is a parabola, but it's not one that we're used to. This one has the squared on the y, which means the parabola will face left or right. So we could have 4 solutions to this system. All right, let's draw that like a circle. We could have 3 solutions, 3 intersection points. We could have 2 solutions, having only 2 intersection points. We could have just 1 solution, or they could have no intersection points, meaning no solution to the system. Now we could solve this system with substitution or elimination. I'm going to solve this with elimination. And looking at my x's, I have an x squared and an x. Those are not like terms, so I can't eliminate the x. But for my y terms, I have a y squared and a y squared. Those are like terms, so I will be able to eliminate the y. So in order to eliminate them, I already have the same coefficient, but I need them to have the opposite sign. So I'm going to multiply by a -1 on the first equation. And that would give negative x squared minus y squared equals -36. And the second equation is y squared minus 2x equals 36. I'm going to rearrange my terms so that the x's and the y's are lined up properly. And that would be negative x squared minus y squared equals -36. And then a negative 2x plus y squared equals 36. So now when I add these equations together, I can see that the x's are not like terms. I can write that as negative x squared minus 2x. The y squareds are like terms, and they are going to cancel each other out. Negative y squared plus y squared gives you 0. And then negative 36 plus 36 gives you 0 as well. I need to solve the equation negative x squared minus 2x equals 0. I never like leading with a negative, so I'm going to divide through by -1. And that would give x squared plus 2x equals 0. Now to solve this, I have only 2 terms, and I'm going to start by looking at what's in common. They both have x's, so I can factor an x out. That would leave me with x plus 2 equals 0. And then I can set each factor equal to 0. And I have x equals 0, and over here subtract 2, that's x equals -2. So it looks like I have an ordered pair solution with x being 0 and an ordered pair solution with x being -2. So now I need to find those y's. Now I can use any of the equations with 2 variables. Let's go ahead and use this one. I have x squared plus y squared equals 36. And if x is equal to 0, that would give 0 squared plus y squared equals 36. Y squared equals 36. And I'll solve for y by square rooting both sides. That gives y equals plus and minus 6. So I have solutions of 0, 6, and 0, negative 6. And then if x is equal to negative 2, I would have negative 2 squared plus y squared equals 36. Negative 2 squared is 4. And I'll subtract 4. And that gives y squared equals 32. I can square root both sides. And get y equals plus and minus. And I can simplify this radical. 32 would be 16 times 2. So 16, the square root of 16 is 4. I have plus and minus 4 square root of 2 as my y coordinates. And that would give me ordered pairs of negative 2, comma 4 square root of 2 and negative 2, comma negative 4 square root of 2. So this has 4 solutions to that system of nonlinear equations. So on this question, we want to graph the solution set of this system of inequalities, which is x squared plus y squared is less than or equal to 64, and x plus y is greater than 6. So I'm going to start with the first inequality. X squared plus y squared is less than or equal to 64. And when we graph an inequality in two variables, I like to do this in two parts, the boundary and the shading. So in order to get the boundary, I'm going to change that inequality sign to an equal sign. So I start with the boundary, and that's with an equal sign. So that's x squared plus y squared equals 64. So this type of equation is in the form of a circle. It's a circle with center of 0, 0 and a radius of 8. That's the square root of 64. Now the boundary is sometimes drawn with a solid line and sometimes with a dashed line. The solid line tells us that the boundary is included in the solution set, and the dashed line means that the boundary is not. In our example, we have this equal to, which is what our boundary line is, so our boundary will be included, and we're going to draw that with a solid line. So when we draw our circle with center 0, 0 and radius 8, it should be drawn with a solid boundary line. So over here, I'm going 8 away from a center of 0, 0. To get a few points on the circle, and we'll draw that circle with a solid boundary line. And then after we've done the boundary, then we want to figure out the shading. So once we draw that boundary line, it divides up our coordinate plane into sections. For the circle, we have a section that's inside. We usually call it a region inside, or a region outside the circle. We need to figure out which of those regions is part of the solution. So to do that, we pick a test point. And there's only one rule with the test point, and the rule is that you cannot pick a point that's on the boundary line. You can pick any ordered pair you want that's not on the boundary line. So lots of people like to choose 0, 0 as a test point because it makes your arithmetic work out very nicely and very uncomplicated. And 0, 0, even though it is the center of this circle, it is not on the boundary line. It's not actually part of the circle. So I can substitute it in and get 0 squared plus 0 squared is less than or equal to 64. And 0 is less than or equal to 64 is a true statement. So that tells me that my test point, which is inside the circle, is a solution. And that also tells me that all of the ordered pairs in that region on the inside are solutions. So I'm going to shade the solutions. All of the ordered pairs inside that circle are solutions. So then we're going to move on to our second inequality. X plus y is greater than 6, and I want to draw the boundary. And in this example, our boundary is going to be drawn as a dashed line because our inequality does not include the equal to. So our boundary is x plus y equals 6, but that boundary is not included in the solution set because we don't have the equal to. So I need to draw that boundary line, and I'm going to draw it by using both the x and y intercept. I can find the x-intercept by letting y equal 0. That would give me x plus 0 equals 6. X equals 6, so I have an x-intercept of 6, 0. The y-intercept by letting x equal 0. That's 0 plus y equals 6, and y equals 6. So the ordered pair 0, 6 is the y-intercept. So 0, 6 and 6, 0 are points on the boundary line, and I can connect those 2 points with a dashed line. So then I need to figure out the shading. So remember, only focusing on that dashed line, we can shade above the line or below the line. And we need to figure out which side is the correct side, the solution set. So we're going to do the shading. We need a test point. You can use 0, 0 as your test point here. So I'm substituting that into the inequality. 0 plus 0 is greater than 6. 0 is greater than 6 is false. So I used this as my test point, and it came out false. So that means that this side that's below that dashed line is not part of the solution set, and it's the part above the line that is. So going above that dashed line, we're going to shade. And so in my picture here, I have shading for the first inequality in yellow, shading for the second inequality in like an orange color, and we do have some overlap. The overlap occurs right here in this little section, and that means that this group of ordered pairs are solutions to both inequalities. So the ordered pairs that we find in that region, trapped by the circle and the dashed line, are solutions to the system of inequalities. We include this solid boundary line, but we do not include the dashed boundary line in our solution set. Thank you for checking out my videos. Have a great day.